Hi everyone, welcome back to Physics 142. It's been a little while, but we've been talking in this course about magnetic fields, forces from magnetic fields, and most recently we've been thinking about torques that you get from magnetic fields. Specifically, we were thinking about the case where if we had a current loop, all right, if we had some sort of closed loop, right? Maybe it's a circular loop, maybe it's a square, it could be any shape, right? But where if you have some closed loop that you run current through, all right? So I'm going to run some current through these loops, right? Maybe run some current counterclockwise here, some current counterclockwise here. What we realized is if we applied a magnetic field across these current loops, so if we imagine some magnetic field here across these current loops, right, here's some magnetic field across this current loop, right, if we applied a magnetic field across that current loop, the magnetic field doesn't actually produce any net force, because if we think about the force law, any bit of current that's flowing, say, so in my drawing here, you can think of this drawing as sort of horizontal to the ground, right? Maybe a little better picture would be like, here's an edge-on view, right? So edge-on, there's my circuit, edge-on, we've got the magnetic field like this, right? There's the magnetic field. And what we realize is, say, any current on this side, right? Maybe if you have some current on this side, it would be coming toward us, right? Usually we represent that as a dot. And if we take the cross product that says we take I times L, the direction of the current and length, and we cross that with B, so we'd have something that's coming up out of the page crossed with B going out of the page, as in my edge-on view here, right? Out of the page crossed with B going to the right, that would be an up force, versus over on this side, it's going into the page, so we point into the page and we cross with B. That is a down force, right? So my right-hand rule demonstration a little tricky here, but the two forces are in opposite directions, so any force that you get on this side cancels with any force on that side, and you get zero net force, but you do get a net torque. And we realized last time that we were able to quantify this net torque, and the way that we could quantify this net torque ended up being the following equation. We wrote down that the torque, all right, the net torque on this closed circuit, the net torque depends on the amount of current multiplied by the area enclosed by the current loop, all right, multiplied by the area enclosed by the current loop, and then we take that and we cross it with the magnetic field. And so remember, I'm writing area here as a vector. How do we define area as a vector? Well, we say the area vector is always perpendicular to the plane. All right, it's always perpendicular to the plane, so perpendicular to the plane here. All right, but it could be going up or down, so the way that we determine whether to draw this up or down, right, which sort of side to make it come out of, is we say whatever direction the current flows, you take your right hand and you curl it around, your fingers around in the direction of the current, and whatever direction your thumb is pointing, that's the direction of the area vector. So, here in the edge-on view, my fingers would curl like this, right? Come out of the page here, and I would get up, right? Here, in my sort of side-on view, they're curling around to the right. So again, an upward-facing arrow there, all right? So the way you determine the direction of the area is by curling your fingers in the direction that the current is flowing, and your thumb will tell you what way to draw the area vector. So this is how we determined our torque. We also were able to write this I times A, gets a special name. It's the magnetic dipole moment and gets drawn with the letter mu. And so we could also wrote this as mu cross B. So that's just a little bit of a review of torque, and I want to do a specific example All right. And the specific example I want to think about is I want to think about sort of this circular current loop. All right. But I want to draw another circular current loop, and we're going to imagine that rather than just having one loop, that it actually loops around 30 times. All right. So here it loops 30 times. And we should give it some dimensions. So we're going to give it a radius. All right. So we'll give our loop a radius. Little r, and we'll say little r, the radius is going to be 5 centimeters, so 0.05 meters. All right, we'll take a 5 centimeter loop. And then we're going to run some counterclockwise current in it. All right, so we'll run some current in it counterclockwise, and the amount of current that we'll run is we will run 5 amps of current through it. All right. Okay, now we want to apply a magnetic field directly across it. So let's take a magnetic field, direct it to the right here. All right, so it's a magnetic field. We'll direct it to the right. There we go. Magnetic field B. And let's say that magnetic field is really strong. All right, so really strong. We'll say that B is 1.2 Tesla to the right. Okay, so that's a really strong magnetic field. And the question is, for this amount of current, if you have 30 turns, how much torque do you get? All right, so we want to find the torque on this loop. So how are we going to do that? Well, we're going to use this formula that we wrote down. Torque is IA cross B. All right. So let's first of all think about the magnitude of the torque. All right, so the magnitude of the torque, well, a cross product is IA, the magnitude of I times A, times the magnitude of B, times the sine of the angle between them, right? Times the sine of the angle between A and B. So for my loop here, this is sort of still a reasonable edge-on picture here, right? A is up, B is to the right, and so the angle between those is 90 degrees. So the sine of the angle between them, right, this is going to be sine of 90, so that will end up just being 1, all right? And we can plug in the other numbers here, all right? So let's plug in the current I. We said that's 5 amps, all right? Confusingly, the units on current and area, I'm using the same letters, right? But this is area. The area of our hoop, well, that's the area of a circle. That's pi r squared, right? So that's going to be pi times 0.05 meters squared, all right? Guess I should add meters there, all right? Pi times 0.05 meters squared. And then so that's the area, and I should note, though, that that would just be the area of one loop, right? If we actually have wire that laps around 30 times, then we could think of each of those circles as sort of adding additional area, right? Each circle, each loop has this area, so we can take this area and multiply it times 30, because we have 30 loops, all right? Sometimes people will represent the number of loops with the letter N, right? So they would say N equals 30, all right? But we can just see that the total area here must be the area of one circle multiplied times 30. So we put in a times 30 to get the area, and then last we just need to multiply times the B field. So the B field is 1.2 Tesla, and then again times sine 90, which is just times 1, all right? We can multiply all those values together, and when I do that, I got 1.41 Newton meters. Remember, that's the unit of torque. But we're not quite done, because torque's a vector, so we know the magnitude, but what direction is this torque going to work? Well, to figure out the direction, we need to do this cross product, right? So we point our finger in the direction of the first vector, that's in the direction of A, so that's up, right? Then we've got our B vectors here are pointed to the right, so I point my other fingers to the right, and we can see my thumb is now pointing into the page. So that means that the direction of the torque is into the page, all right, into the page. What does an into the page torque mean? An into the page torque means that that's your axis of rotation, so it's going to rotate around axis that points into the page, and you might recall from Physics 141, the right-hand rule that we used there is if you take that axis of rotation, you put your thumb around it, your fingers will curl in the sense of the rotation, right? So if we have into the page rotation, into the page, that means that this part will start going up and this part will start going down. That's what an into the page torque would mean. So there we have an example. The other thing that we could mention is that if you know the torque and you know the moment of inertia, then you can figure out the angular acceleration, right? So we might recall from Physics 141 that torque is the moment of inertia, which confusingly also gets the letter I, so you have to know the context, right? The moment of inertia I times the angular acceleration alpha, right? And so if we wanted to solve for alpha, let's say that we knew the moment of inertia. Let's say we knew the moment of inertia was 1.0 kilogram meters squared. All right, let's say that was our moment of inertia for this hoop. All right, then we could figure out the angular acceleration. We would just take torque and divide it by I, and that would give us alpha, right? The direction would end up being the same, and we would just end up with that alpha is 1.41 1/2 squared, radians per second squared, and also into the page. I should comment at this point in the video that one thing to keep track of is we now have sort of 3 different right-hand rules that we're using, and so I think it's important that I clarify those different right-hand rules, right? So one of the right-hand rules that we're using is we have the right-hand rule that just says that if we want to know the direction of things like angular acceleration or the direction of rotation of something or of angular velocity, we realized that if you curl your fingers in the sense of something rotating, right? You know, if I take my pen and I rotate it like this, right? I curl my fingers in the sense of that rotation, your thumb points along the axis of rotation. So that's sort of right-hand rule number 1, I think we said last semester, right? Is that you curl your fingers in the sense of rotation, maybe counterclockwise, your thumb points along the axis of rotation. We also have the right-hand rule when you have 2 vectors and you take a cross product, right? That's the point to the first vector, curl your fingers to the second vector, and the answer is the direction of your thumb. And we also now have introduced sort of a third right-hand rule that says if you want to know the direction for an area vector in a current loop, all right, or we could also say the direction of that magnetic dipole moment, right, because those are the same thing, the direction of the magnetic dipole moment, well, now we're going to curl our right-hand fingers in the direction of the current, and whatever direction your thumb points gives you the area vector. So we've got a couple different right-hand rules, right? When in doubt, use your right hand and curl some fingers in, whatever direction things are going, and that will probably be the way that things work out. So, but just something to keep track of here. We will do another example and think about some applications of this torque in the next video.